Personal experiences during many years of Lenr experiments.
I think right now in cold fusion we're over here. We're able to make enough heat. We're able to almost generate electricity using thermoelectrics. We're way past here with the demonstrations. We've shown reproducibility. And the one thing we haven't quite hit is to get the feedback on the electrical loop. And that's what we're working on. Now, at JET, what we've been looking at is techniques which were first developed at the Laboratory of Insulation Research at MIT to characterize specimens using dielectric spectroscopy. And then the effort was to maximize incremental power gain and the total output. And I've tried very hard to add additional diagnostics. And that's been rather easy because, of course, since cold fusion's developed, we now have digital sensors. We didn't have them then. We have small microcomputer devices, which we didn't have then. And as a result, a number of things happened that I'm putting them over here. And it's been a long haul. And hopefully, next year, we'll begin possibly having an advanced course. And at the end, I'll show you what we're thinking about, trying to put some of these very low power, hopefully electrically producing devices in space or for QRP measurements and some other things. So when cold fusion started, my first emotion, unlike all the nervousness I showed last night, was astonishment. I mean, imagine cold fusion in your house. And I began thinking about it because classically in electrochemistry, everybody used the Nernst equation. And at MIT, we were pushed to deal with the Navier-Stokes. And that lets us do solutions non-equilibrium. Okay, and the other thing I tried to do was, you know, there's only a gate here. I've never figured out why the sheep act as if there's a gate here. We've tried to look in other directions where people weren't looking, high impedance cells. It seemed to me that everybody was salting solutions everywhere. And yet when I took the salt out, I got maximum gain. In fact, at the demo that we showed at MIT, the heavy water cell had 800,000 ohms. And in fact, when we make the L.e.n.rs, it's even higher. Now, this is me back in 1969 in Arthur von Hippel's lab. This is today at my home. It doesn't seem much different. And this is L.e.n.r helping out, running a test that we'll show you later. And one of the questions people ask me is, why do you have so many power supplies? And the answer is, I try to match the impedance between the power supply and the cell. And you all do that, right? Okay. The second emotion I got was awe of how fantastic you people are. And I started to report it in the Cold Fusion Times. For 12 years, we put out this 12 to 25-page journal. It came out between bi-monthly and quarterly, and here's L.e.n.r. I managed she was very kind to augment. She had worked for 20 years in national magazines, including People and other things, and now she was helping us write for Cold Fusion Times. So we kept going on for the 12 years, reporting bi-monthly or quarterly, as I say, and for me it was terrific, because I could find out what was going on, I could interview the people, call them up, and it was a terrific way, in fact, of sharing the information with everybody else in the field. So I was astonished. Everybody says it doesn't work, it's not reproducible, and yet here it is, issue after issue. People are getting reproducibility, people are seeing helium, people are clearly seeing what's going on, and of course this was a patent war that created the problem when Patterson sued Fleischmann, and we covered that. We tried to cover everything in these pages, and I couldn't believe, by writing this over and over, how much material was being done. And then there was admiration, because, I mean, I'm speechless how much information was coming out of experimental work in this field. And then there was amazement. There was that 2 a.m. call. Gail picks up the phone. Sri Lanka? And it was amazing. We've had so many people come in from the outside helping us, and of course that was Arthur C. Clarke. And then there was disgust. MIT, as you know, had done the Plasma Fusion Center curves where they did the light water curve and the heavy water curve. And of course, this was what they measured. This is what they reported. And Peter yesterday mentioned how they gave me the data. They didn't do that until they were directed by the president of MIT. And in looking at their data, they had 9 different curves for the heavy water curve. 9 curves for the same experiment. And when I corrected what their original data was, by gosh, they got the same excess heat Fleischmann ponds got. They got it at the same time. And I gave this to President Vest, and he kindly got Philip Morrison, the Philip Morrison, to confirm it. And he went through the data, and in fact, he agreed. MIT in the heavy water cell got 15 milliwatts, and the light water cell got 4 milliwatts excess power. Now that's interesting because every one of you who's filed for a patent has been told by the US Patent Office they didn't get anything. Now what's most irritating to me is that Philip Morrison asked MIT to withdraw the paper, and they never have. Okay, another emotion I've had is surprise. I applied the quasi-one-dimensional model of isotope loading, and to my astonishment, it taught us how to do cold fusion, how to control excess heat, and that was, I don't want to go through the equation today, it's the only equation. But the important point is, everybody says cold fusion is fusion by electrolysis. Well, that ain't exactly right. It's 1 minus electrolysis. This is the first-order gas effect. And in fact, the entry rate of protons or deuterons into the palladium is forced in by the electric field and the electrophoretic mobility, minus what goes up in the gas. Anyway, I talked about this the other day. I won't go through it again. A lot of things came out, and that was terrific. The other thing was happiness, because as a result of doing this, we were able to make reproducible, high incremental power gain for the aqueous. It varied between 5, and we had one as high as 20. And here's the first fusors that we began making. We developed them over time. This was the one that I showed at MIT. This is one that we irradiated with a laser. We reported that at ICCF-10. And we reported in the paper how to set these up yourself. Now, one of the really interesting things about doing cold fusion this way is you don't get bubbling on both sides of the cathode. And I remember Mike interrupting me in ICCF-10. He goes, no, that's not what happens. And then I pull the slide out, and we have a whole demonstration. When we get excess heat, this is what we see. And I won't go through this. This is what we talked about last time. The classical way is to use 2 wires. And in fact, what we do ends up putting a flux through the metal. And in fact, we've learned how to control the failure that occurs, because once you get gouts of bubbles coming out, the excess heat shuts off. And that's why I presented the 2-state issue. The fact that if you really want to drive these systems well, you've got to keep it out of the state that collapses the excess power. This is a dual anode fusor type component. We got 80 times input with a fusor, and I always do all my controls. And the people who say my stuff is complicated, we use DC and we use ohmic controls, and I'm sorry, it scares them. Here we see the control with the laser. The excess power is seen here, and we always plot the energy to the right. So here you can see this is the excess energy that developed. And the other thing that's interesting, if you look at the slopes on energy, when you get excess heat, you always have a rise in slope between the ohmic control, as opposed to if there's no excess heat, they're parallel. So finally, we learned how to control also heat after death, and we have these nice curves where what we have is 2 containers. So we have 2 ohmic controls, 1 ohmic control in the second container, 1 ohmic control in the first container that we alternate with the active cell itself. So here we see the controls, and the input power matches the output power. And in fact, here's the energy, and I think you can see them. They don't quite overlap. And here's our input to the fusor type component. So here is our excess energy, and then we're even able to measure the heat after death. The optimal operating manifolds. The first time we did this, I was astonished. I tried to scan, as a function of input power, these devices in this aqueous system. The first time we did it, we got one dot above. Then I looked closer, multiple dots above. And pretty soon we realized if anybody's driving it here, they're not going to get anything. If anybody's driving it here, they're not going to get anything. And we learned that if you want to characterize a sample, you really have to scan it, find out its peak, and then you can begin to compare additives, components, and systems. Here's some more optimal operating points. I was very interested to spend quite an amount of time to determine the fine structure of these. So here we see the controls. Here we see for the diffuser type component, we have minimal loading here, more loading here, and here I think we're getting wasteful electrolysis. And that's the same thing as the area that I showed you when you go into loss of aerodynamic flight. And we see these optimal operating points rise with time. Here's a co-deposition experiment. Mine are a little bit different from the others. What I do is I do co-deposition, build up, and then I no longer deposit any more material because we find that decreases the amount of excess power we can get out. So here we're getting out about 2.5 watts excess power. Ed told me we don't see it, so I looked at his data, and his data showed the same thing. So was it a time to go public? I wasn't sure. G. Maliv came by and looked at our cell, and this was the run that he saw, and this was his run. This is the ohmic control, input power to the diffuser type component, output. So the difference here is our excess power. The difference here is our excess energy. And we know the whole thing is working because we've matched by an ohmic control. Gene was happy. It was one of the nicest smiles we ever had out of him. And this is all over the internet, and it happened about 15 minutes after we got the excess heat. So he came back with a cake and congratulated us for getting excess power. And then there was the horror, because as a result of having the excess heat, we called Popular Mechanics, and they promised to come by on Sunday, and Gene was murdered that Friday. A few months passed, and I was delighted to have Brian Josephson come by. And this cell had been running for months. We had done it at MIT in 2003 at ICCF 10. Could somebody get me a glass of water? I'd really appreciate it, thank you. And this is Brian Josephson's run. So again, we do ohmic control. Here we do the diffuser type component. Here is our ohmic control for energy. And here is our input to the diffuser cell. Here's the output. And the information's over here of how much he got. Heat after death was 270 joules. And I can't read the rest, but it's all there. And what was terrific was, here again, we see the importance of optimal operating points. We're getting gains of 1.5, 1.6. Thank you. Thank you. Thank you. Okay, so the next thing is applications. What can we do for diagnostics? I apologize to all of you. I filed a patent on measuring loading by vibration of the cathode. And those of you who know physics, freshman physics, you know that the angular frequency goes as the square root of k over m. So I thought this was a terrific thing. We were measuring it. The patent office called this cold fusion. And this was the patent that is cited in INRI Swartz and called cold fusion. It is a method to measure loading, and they just lied about it totally. Then we decided to develop methods to improve calorimetry, and we do three-pole calorimetry. I'll tell you what it is briefly. Depending how many input points you use in your calorimetry, for example, if you use just a CBEC, you're going to get this curve. You're going to have to wait a long, long time. Here we have an ohmic control. Here we have the cell. What we learned is, in addition to using, for example, a CBEC or its equivalent at the boundary, what you really also want to do is use Newton's law, T1 minus T2 from the center. That'll get you to two-pole calorimetry. And the advantage of that is when you do the energy, it won't go negative. which would mean your algorithm's wrong. And 3-pole is Newton missed. There was another term. In addition to T minus T2, the inside minus the outside, there's actually a term T1 plus T2. And that has to do with the mass, the thermal mass of the calorimeter. And if you add that in, darn, you get a pretty good response. So that's what we use, 3-pole calorimetry, and that's our secret that we use to make these come out so well. The other secret we use is lots of controls. We use thermal controls, dual ohmic controls, that is paired calorimeters. We use metallic cathode controls, not often, but sometimes. We do a variety of ways to make sure we have calibration and corroboratory methods. This is the dual ohmic control. This is the one we showed at MIT at ICCF10. What we do is we have a current source, we put it through the cell, we put it through the ohmic control, in series, electrical series that comes back. And what you don't see in this picture is that there's a calorimeter around each of these devices. It's easy to measure voltage. The current's the same. So in fact, we clearly know the input power, and the differential temperature was always higher over the cold fusion cell. And so I think this was actually the simplest way that we can show excess heat. All right, Spay came out with this beautiful result showing flickering over a cathode, and I looked at it and I'm thinking, they really don't have proof that that's excess heat. So let's see if we can do it. So we set up a fuser type component. I ended up making, they were using far IR. I didn't have the money for that device, so if any of you want to know how to do it, you can take any cam and make it into a near-IR system. So that's what we did, and we're looking at the near-infrared here. And to my astonishment, to do the calibration, we needed 2 controls. I thought we would have 1, but once again, you're going to have more controls than you think, and in the end, we were able to show that when the fuser-type component was coming, we had a lot of near-infrared coming out. Anticipation, we put on the colloquier and the IAP, thanks to Peter Hagelstein. And I must admit, I was a little nervous there. This is some of the long, hard work we did. By now, once we had the fusor-type components, how can we drive some motors? So my plan was to put paired Stirling engines in 2 boxes, and nobody's ever seen the inside. I'll show you now for the first time. What we do is we put 1 cell in each of these boxes. We mount the Stirling engines on both, and we're able to show, as we showed to Dikr, which opened up proposals to the United States, motors. Again, we have the current going through, the same through both. We worked it out, in fact, so the power was the same through both. The ohmic control just sat there, and the cold fusion component was spinning. And I think that's actually what really impressed them at Dikr. We've tried hard to close the loop. How, with this heat, can we now make electricity? So I'm not going to go too much into this. We've tried making cold fusion cars, done preliminary work with that. We've actually tried to make cold fusion-driven drones. We call that Project LEAP. We'll talk about that next year. We've tried to twice now, once in '96 and once in 2006, I think, just before ICCF 14, tried to make the loop. And I was astonished. We were getting losses in the wires, losses in the switches. When we go back this time, I think we're going to know how to do it because we know where the problem points are. Yeah, I had nervousness. When we did the open demo in 2003, I think that was one of the scariest times of my life. Peter thought I was going to have a heart attack, and I'm not sure I wasn't close. But it's a performance anxiety. And it probably was worth it because taking the device back from MIT, it spilled. And after that, I learned an important thing. If you're going to take your system and show it somewhere, practice moving it to a few places before you take it there and learn what the weaknesses are. Anyway, we did have good open demos. This was the demo. This was for the Lenr type component at MIT during the IAP. This is for the aqueous systems at ICCF 10. And Triumph, when we got the Stirling engines data in front of Dikr, with Dave Nagel and Mike Melich and other people, they accepted proposals. And I was very delighted that how could we take some new technologies, because 3D printing's come out. How many of you have 3D printers? Well, that's going to change after this. I use 3D printers all the time. My wife was kind enough to let us take one bathroom and just fill them with 3D printers. So I'm totally happy. We've used them to make various types of NANR configurations. We didn't use these because we didn't like how they looked and worked. You can buy filaments of glass, polypropylene, all kinds of plastics, metals. I'm going back after this meeting and getting magnetic materials. And here's some that change color. So there's even a way you can make a platform for your experiment and measure maybe the heterogeneity of temperature on the surface, and you can record it with the color changes. We have new components coming out. We got Series 10 we're putting in these, and we're making calorimetric. There's nothing you can't do with this stuff. Poor Midas, he only had gold. For example, the discussion was, could we do Raman spectroscopy? So it took me a week to print out a Raman spectrophotometer. I bought the optics. You know, what a world. You go on eBay, you can get anything you want. You go to one country, you get the best gratings. You go to another country, you can get Herbert Smithite if you want it. It's just amazing. So we were able to make this device where we could put the NANR type component here, irradiate it with two coherent systems, and as you saw, what we see is without any electricity, we see this. In avalanche mode with no electricity, we see that. And if we're getting excess heat, we see this. And in our second paper on this, we identified each of the peaks. And this is a terrific way because this occurs immediately. You don't have to wait. I mean, if you've got a Seebeck calorimeter, I don't think it's that good anyway, if that's the only thing you're using, but you're sitting there for hours waiting. Put one of these on, you'll know right away. I've been astonished. You know, we started off using thermocouples, thermistors, RTDs. Everything's different now. Now you can buy digital devices and you can write in C to have them measure maybe 50, 100 times a second, average the data, and we were able to take data and decrease noise by 29/30ths by taking microelectronics, putting it in the temperature sensor, and then sending the digital signal. No more QRM, that's man-made noise or atmospheric noise. Another emotion. There's been a lot of sadness and nostalgia. We've lost so many people. I don't actually think we've ever had a moment of silence for anybody. Do you mind if we do that for a second? There were so many friends that I really loved in this group, and they passed. So maybe we could just take a second and think about them.
Please include Arata, who just passed away as well.
Okay, thank you. Here's where we are today. This was the ICCF-10 fusor type component, though this is the ohmic control. That just shows the size. And these are our new MOACs, mother of all cathodes, which this one was built at MIT, made out of a half a mile of nickel wire. And my interest, if any of you are interested in helping us, is making one of these out of deuterium and palladium. And my calculation is if we get excess energy out of that, there'll be enough deuterium to last more than 10,000 years. Maybe by then we'll be able to convince the skeptics. The other thing we're trying to do is put the nanors into what we call nanosats. There's a big interest now, though the FCC clamped everybody down for a while, of putting tiny devices into space. Because our cell phones, look at what we do with our cell phones. We can measure magnetic field, temperature, image, and it keeps expanding. So why not put them into space? Why not everybody's been thinking about big rockets, big machines, but these we might actually be able to accelerate with radiation from Earth. Anyway, it's been an incredible 29 years, And I got so many people to thank, I mean, it would just go on. And thank you. Thank you, Mike.
Thank you very much, Mitchell, and thank you for getting us on schedule. There's time for a comment or two.
Thanks a lot, Mitch. Just a comment about 3D printing. If you want to use 3D printing, you don't need to own the printer anymore. There are many services like Shapeway where you can just send your 3D file and you get your part 1 week later. And you can print plastic parts, but you can print any kind of metal. You can print ceramic parts and just do whatever you want.
You want it yourself. You used to buy printers from Hewlett-Packard for $1,000. Now you can have a dual extruder printer for $600, the same one they have in the space shuttle. And in the week that you're waiting to get that part, you can do 6 iterations a day.
I have a quick question on the patent department. I have always found them very rational, although they go off the deep end at times. There's a patent on an electric car with a windmill on the top recharging the car, and they granted that patent, but somehow cold fusion has been a dead end. What the hell's going on? Who stopped them and why?
Wouldn't that be good to know? Why? You know, they say we have no reproducibility, but they issue patents in astrology. I've never figured that out.
Thank you very much, Mitch. And I invite